Okay, good afternoon, dear student. In last class, yesterday class, we discussed the heterops and definition of transport number and heterops. Okay, in today's class, I am going to discuss about the applications of conductance measurement. That is a conductance measurements. Here, the applications, there are 5 applications for the conductance measurement. You already know the equivalent conductance and molar conductance and another specific conductance. The unit name is conductance. Heading is the applications of conductance measurements. The applications of conductance measurements. Conductance measurements. First one, the determination of equivalent conductors at infinite dimension. First one, the determination of equivalent conductance. The determination of equivalent conductance at infinite dimension. At infinite dimension, lambda, it is denoted, that is infinite dimension for a weak electrolyte. For weak electrolyte. For weak electrolyte. Second is a determination of ionic conductance and absolute velocity of ions, that is ionic mobility. These two are, you all already know, you studied in Coldrax lab, the application of Coldrax lab. Here, these are the applications conductance measurement. Second one, determination of ionic conductance. Determination of ionic conductance. Ionic conductance and absolute velocity of ions. The absolute velocity of ions and the absolute velocity of ions, that is ionic mobility. Ionic mobility. And third one is the determination of degree of dissociation of a weak electrolyte. Third one, determination of Determination of degree of dissociation. Determination of degree of dissociation of an weak electrolyte. Determination of degree of dissociation of an weak electrolyte. Electrolyte. This is a third. And fourth one is determination of dissociation constant of a weak acids. Determination of this is the degree of dissociation. Here you get some formula and then you add this value in the dissociation constant. That is the determination of dissociation constant of weak acids. Determination of dissociation constant of weak acid. Constant of weak acids. That is here denoted as Ka or Kb. The degree of dissociation constant is denoted as Ka or K. And fifth one, the determination of the solubility of a sparingly soluble solvent. Fifth one, the determination of the solubility. The determination of the solubility of a sparingly soluble solvent. Or sparingly soluble solvent. These are the 5 conductometric applications. And here the first one, equivalent conductance. Equivalent conductance here, the equivalent conductance of weak electrolyte at an infinite dilution. It cannot be determined directly. Here you know this is the equivalent conductance at infinite dilution. The equivalent here the determination of the equivalent conductance. The determination of the equivalent conductance at infinite dilution for a weak electrolyte. You take any of the weak electrolyte. Here the acetic acid versus the weak acid versus weak base. Ammonium hydroxide. The weak bases are the ammonium hydroxide, and here the weak acids or the acetic acid. And strong versus strong base, here sodium hydroxide, and another the sodium hydroxide is a strong base, and weak acid, strong acid is a HCl. You take strong versus strong, weak versus weak, strong versus weak, and weak versus strong. Here this is the types of the conductometric measurements. And here the application is the determination of the equivalent conductance at infinite dilution, lambda not for infinite, right? That is lambda infinite. Infinite dilution is 0. Concentration is decreases here. It is denoted as lambda naught, and for a weak electrolyte. I explained this determination of equivalent conductance at infinite dilution. This determination is not determined direct method, it is an indirect method. Indirect method is only Colbert's law. In that Colbert's law, I discussed this determination of the equivalent conductance at infinite dilution for a weak electrolyte. And second one, determination of ionic conductance. Determination of ionic conductance also, I discussed the determination of ionic conductance and absolute velocity of ion, that is a ionic mobility relationship here. The determination of ionic conductance, the relation between here, the relation between ionic conductance and the ionic mobility. Ionic conductance and ionic mobility, you have one formula. The ionic mobility is equals to ionic conductance divided by 96,500. Here the determination of ionic conductance and the absolute velocity of ions. Absolute velocity here, the absolute velocity of ions, that is ionic mobility here. These are two are the relation between them here, the ionic conductance and the ionic mobility. The relation between the ionic conductance and ionic mobility is the ionic mobility is equals to ionic mobility is equals to ionic conductance is equals to ionic conductance divided by 96,500. This is a relation or formula, ionic mobility. Relation between ionic mobility formula. Relation between ionic mobility and ionic conductance formula here. The ionic mobility is equals to ionic conductance divided by 96,500. And this is also I explained in the Colbert's law application here, the Colbert's law. This is the second determination. Next, third one, that is a determination of degree of dissociation. Here, the determination of degree of dissociation. Determination of degree of dissociation. Dissociation. This is determination of degree of dissociation. Of an weak electrolyte. Degree of dissociation of an weak electrolyte. Here, the degree of dissociation of weak electrolyte is denoted as alpha. This is denoted as alpha, and the degree of dissociation of weak electrolyte is alpha. It is given by the formula as alpha is equals to lambda c divided by lambda naught. Lambda c divided by lambda naught. This is the formula of degree of dissociation of a weak electrolyte. Here the lambda c is the equivalent conductance. Equivalent conductance. Lambda c is the equivalent conductance at zero concentration. Lambda c is the equivalent conductance at the here c is the for this one at zero concentration, and this one is at concentration. Here the equivalent conductance at the concentration at the concentration And the lambda naught, that is zero concentration or infinite dilution. Lambda naught is the, here this is the equivalent conductance of at concentration C is denoted at concentration C, and here the lambda naught is also equivalent conductance at a zero or infinite dilution. Here where lambda naught is equals to, lambda naught is equals to equivalent conductance or equivalent concentration at G. This is the equivalent concentration at 0, or it is an infinite dilution. 0 concentration or infinite dilution. 0 concentration or infinite. It is denoted as infinite dilution or a concentrate zero concentration. And the lambda Cn, lambda naught, and alpha is can be calculated for you are doing experiment. The determination of degree of dissociation of an weak electrolyte, you are using this formula. Alpha is equals to lambda C by lambda naught, and lambda C is the equivalent conductance at concentration C, and lambda naught is the equivalent concentration at zero concentration, or equivalent conductance at zero concentration or infinite dilution. And here, knowing the value of these three, calculate this determination of dissociation of an weak electrolyte. You have determination of this dissociation of weak electrolyte using the conductivity bridge. Use the conductivity meter, and find the dissociation, degree of dissociation of a weak electrolyte values. This is a second one, second application. Sorry, third one. Third is a completed. And fourth one, the determination of dissociation constant. Fourth one is a determination of dissociation constant. Dissociation constant of a weak electrolyte, that is a weak acids. Dissociation constant, determination of dissociation constant, and it is denoted as K or KD. The determination of dissociation constant of a weak acid. Weak acid. Or you write weak electrolyte here. Weak acid, determination of dissociation constant, and here the relationship between the dissociation constant Ka and degree of dissociation alpha. Here the degree of dissociation is denoted as alpha, and here the dissociation constant is denoted as Ka. And these two relation here, these two are the relation between them, and the formula is Ka is equals to alpha square divided by 1 minus alpha into concentration. This is concentration, alpha square divided by 1 minus alpha. This is the formula of finding the dissociation constant of a weak acid here. K is equals to dissociation constant. Alpha is the degree of dissociation. C is the concentration. Here, you know this one, this degree of dissociation value. You can calculate this dissociation constant. You know degree of dissociation value, it is very easy to calculate the dissociation constant of a weak acid. And alpha is obtained. The relation is alpha is equals to lambda c by lambda naught. You know the lambda, this one alpha is equals to lambda c by lambda naught. You calculate this value and you get this alpha value, and this alpha value substitute in this equation, and automatically you get this dissociation constant of a weak acid. And here is denoted as the equivalent conductance at constant concentration. Concentration is constant. Concentration is constant C into lambda at constant concentration, and it is can be obtained using the relation, that is lambda c is equals to lambda c is equals to k into 1000 divided by k into 1000 divided by you get this is a concentration. Here the equivalent conductance at concentration constant C into lambda C, and using this equation and you get lambda C is equals to K into 1000 divided by C, where here this K is a specific conductance. Specific conductance. Here. This is a specific conductance. Here you get this is a alpha. Alpha is equals to lambda c divided by lambda naught. This is a degree of dissociation, and degree dissociation constant is, that is Ka is equals to C into alpha square divided by 1 minus alpha. This is a dissociation constant formula. Here this is a concentration, this is a dissociation, degree of dissociation, and here alpha is equals to lambda c divided by lambda naught. Here you know the lambda c value is the lambda c is constant, here concentration constant is C into lambda c. Here lambda c is equals to, the equation is K into 1000 divided by C. Here 1000 divided by C, and here the specific conductance is this K is a specific conductance. When you calculate this value, you get a equivalent conductance of a concentration, and this value you add in this formula. Alpha is equals to lambda c divided by lambda naught at infinite dilution, that is infinite dilution is 390. Here the infinite dilution is 390. You get here something values, and this value substitute in this formula, and here divided by 390 you get a dissociation, degree of dissociation, and you get degree of dissociation. You can easily calculate this dissociation constant, that is K is equals to C alpha square divided by 1 minus alpha. This is the fourth application. Next, fifth one, the determination of the solubility of the sparingly soluble solid. Fifth one, determination of the solubility of the sparingly soluble solid. Solubility, determination of the solubility of the sparingly soluble salts. Sparingly soluble salt. Here the sparingly soluble salts as the silver chloride. The salts is here. The determination of solubility of the sparingly soluble salt. The salts are the silver chloride, barium sulfate, silver chloride and barium sulfate, etc. Silver chloride and barium sulfate and another lead sulfate. You take another example, etc. PbSO4. This is a lead sulfate and this dissolved in water to very small extent. These are dissolved in water very small extent, and that is here these salts are, that's why these salts are called as sparingly soluble salts. These are the here these salts. One is a silver chloride, another is a barium sulfate and another is a lead sulfate. These salts dissolved in water. These dissolved in water very small extent. Very small extent. Very small extent. These are dissolved in very small extent in water, and that's why these salts are called as a sparingly soluble salts. Here, these dissolved. This means these salts, that is sparingly soluble. These are the sparingly soluble salts. One is here barium sulfate, and this barium sulfate is dissolved in water. It dissolved in water very small extent. That's why these salts are called as sparingly soluble salts. This is a definition of for sparingly soluble salt, and it is very small quantity, very small extent. It dissolved very small extent in water, because of it is known as a sparingly salt. And the solubility of each salts can be calculated by the application of Conductance law. You are use the application of Conductance law. You are finding this the determination of the solubility of the sparingly soluble salt. You are using Conductance law and the conductance measurements. Here, the specific conductance of the solution. Here is supposed to the K is denoted as a specific conductance, and the solubility of the salt is gram equivalent. Right here the formula of this sparingly soluble salt, that is equivalent conductance of the solution. Here the sparingly soluble salt, the solubility of the salt in gram equivalent per liter, the gram equivalent per liter, then the volume of the solution in cm3, that is cm3 or dm3, containing 1 gram equivalent will be 1000 divided by here dissolved, that is sparingly soluble salt, then S is equals to 1000 into K divided by lambda naught. This is the formula. This is the determination of the solubility of the sparingly soluble salts. Here the equivalent conductance of the solution. Equivalent conductance, therefore this is equals to the specific conductance into 1000 divided by s. Equivalent conductance of the solution, therefore is equals to specific conductance into 1000 divided by s. And here the equivalent conductance of the solution is lambda, and therefore is equals to, the specific conductance is K, and here 1000 divided by s. Here the specific conductance lambda, therefore this is equals to equivalent conductance lambda, and here specific conductance K multiplied by 1000 divided by s. And here then it is modified here. It dissolves very little solution here. It dissolves very little solution, diluted or very little solution. The solution is very dilute, so that the lambda, that is equivalent conductance is considered as equal to the lambda naught here. That is equivalent conductance at infinite dilution. Finally, you get the equivalent conductance at infinite dilution. That is, here you take this S is equals to K multiplied by 1000 divided by lambda. This is a formula for finding the sparingly soluble salts. This S is equals to K into 1000 divided by lambda, and according to the Coldrack's law, here the value of lambda naught can be application of Coldrack's law. For example, for here the silver chloride. Silver chloride is Ag plus, for application of Coldrack's law is written as lambda naught. Therefore, this is equals to lambda here. Lambda, silver chloride means Ag plus and Cl minus. Plus lambda Cl minus. According to the Coldrack's law, here the lambda naught is equals to Ag plus Cl minus. This is the Coldrack's law. And here this will give the solubility in gram equivalent per liter. You are giving the gram equivalent per liter. The solubility in grams per liter can be obtained by multiplying S with the equivalent weight of the substances. Here multiplied with S, and it is the equivalent weight of the substances, and here therefore this S is equals to K into 1000 divided by lambda. This is a fifth application, that is the determination of the solubility of the sparingly soluble salt. Okay, next the salt particles. Only important in the applications of conductance measurement, sparingly soluble salt. A determination of this sterile soluble salt. This is a 3 to 4 marks important. Analyze this question. Explain the determination of sterile soluble salt. Okay. Next, the salt hydrolysis. Next, the salt hydrolysis. This is also 5 marks question. Salt hydrolysis. Here, the salt hydrolysis, some extent on distribution line. Here, the salt hydrolysis is defined as the process in which the salt reacts with water. This is a process. The salt is salt and hydrolysis is given to water molecule. Here, the salt hydrolysis is a process and in which a salt is reacts with water to give a back the acid and the base. Here you are giving the acid and base back here. This process is known as a salt hydrolysis. Here salt, and write the general equation here, salt plus water, salt plus water to give acid plus base. This reaction is known as a salt, this process is known as a salt hydrolysis. Here salt is reacts with water molecule to give a acid and base is called as a salt hydrolysis. And here I take salt is Ba, consider here Ba plus water molecule plus water molecule plus water to form acid is Hb plus base. Acid is formed and base is right BOH and base is formed here. This is a salt and here this is salt, this is water and this is acid and this is base. Here it reacts with acid here H, this reacts with water H and finally it gets OH hydroxyl group is reaction this. And for example, you take salt is a NaCl and water H2O and formation is here there is a salt plus H2O and gives the acid and another that is a base. And here they all salts are strong electrolytes and thus they ionize completely in the aqueous solution. This is also very important salt hydrolysis. In the aqueous solution, if the acid, that's with hard acid here, HA here, hard acid, and process is strong, and the base OH process is a weak here. Strong acid, weak base. You can write this reaction is a B positive. A is a negative. A is negative. A is negative plus water molecule H2O and here the formation, this is a positive and this is a negative. This positive and this is a negative. These two are reacts with water molecule to form H plus. Here the H plus and here A minus and BOH. H plus plus A minus plus BOH. Here the OH hydroxyl group is attached and here the hard acid is formed here and with base here this base is formed. And then you write B positive or another fold B positive plus water molecule to form H plus and BOH. B positive plus water molecule. Here one hydrogen is present, H plus BOH. This process is also that is salt hydrolysis. Here in this the only you taken B positive base here the B positive. This is a cation, and here in this case the cation is this is the anion, this is a cation, and this cation is reacts with water molecule or water to give the acidic solution here. This cation reacts with water molecule, it gives the acidic solution, and this is known as or this is called as a cationic hydrolysis. This process is called as a cationic hydrolysis. Cationic hydrolysis. Next here the product acid is formed, that is product acid produces that is a weak acid, and the base produces a strong. When here afterwards the weak acid and strong base, weak acid and strong base, you will take another reaction or you react with cations and anions B positive and A positive. The formation of that is a weak and strong base. Here B positive plus A negative. This is a cation and this is a anion. These are reacts with water molecule plus H2O, and this formation is that is a weak acid, that is HA plus B positive plus OH minus. Here the B positive plus OH minus. Then it reacts with anion. This one anions reacts with water molecule to form here. This process is known as the anionic hydrolysis, and formation is HA. Here one H is replaced here. This attack this one A, and here HA is formed plus another only remaining is OH minus. Here the OH minus is remaining, and the anion reacts with water molecule. This anion reacts with water molecule, and it gives the basic solution, and this is known as a anionic hydrolysis. This is known as a anionic hydrolysis. This is known as anionic hydrolysis. And here the salt hydrolysis may be defined as the reaction of cation or anion of the salt with water to produce acidic or basic solution. Here finally this salt hydrolysis definition is defined as, right here, definition is defined as, here it reacts with cations and anions. Defined as the reaction of the cations, reaction of the cations and reaction of the cations or the anion of the salt, and anion of the salt or anion of the salt, anion of the salt to form or to give the acid and base. To here is defined as reaction of the cations or anions of the salt with water, right? anions of the salt with water. And the salt with water, H2O water, right? With water to produce the acid and base. Here the formation is acidic and basic solution. To produce acidic and basic solution. Basic solution. This is known as a salt hydrolysis. Here acidic or basic solution. Acidic and basic solution or acidic or basic solution. This the salt hydrolysis. I will stop here only. I will continue in the next